Welcome to This Explainer. Today we're exploring a world that honestly sounds like it belongs straight in a sci-fi novel. We constantly hear about the absolute magical promises of quantum technology, right? We're talking computers that are going to solve impossible problems in seconds, and sensors that can literally map the invisible forces of our universe. But what rarely makes the front page headlines is the gritty, physical reality of how these machines actually operate. Behind all that mind-bending math and the shiny gold chandeliers of quantum processors, there's a hidden engine making the whole shebang possible. It's a technology that is, for sure, the unsung hero of the quantum realm, and today we're going to unpack exactly what that is.
So let's just dive right in by asking kind of a weird question. What does a revolutionary quantum computer have in common with an MRI machine at your local hospital? I mean, at first glance, they seem completely worlds apart, right? One is the absolute bleeding edge of computer science, and the other is a pretty standard, albeit advanced, medical diagnostic tool. But if you look a little closer, they actually share a crucial, freezing cold secret. Both of them completely rely on the mastery of cryogenic technologies to function. Without extreme, profound cold, literally neither of these incredible machines could do their jobs.
To really wrap our heads around why, let's draw a pretty stark contrast. Think about your everyday desktop PC or your laptop. It uses a simple spinning fan to blow air across a heatsink, basically just keeping the silicon chips cool enough so they don't melt on your desk. It's a total brute force room temperature solution. But a quantum processor? Yeah, you can't just slap a desk fan on it. It requires supercooled superfluids to reach temperatures that are roughly 100 times colder than a single degree past absolute zero. We are talking about environments that are significantly colder than the vacuum of deep space itself.
Okay, so why go to such absolutely extreme lengths? Well, it all comes down to what we can call the quantum catch. Quantum states, those delicate superpositions and entanglements that give these systems all their crazy processing power, they are notoriously incredibly fragile. In the quantum world, any environmental heat or electromagnetic interference acts like this deafening, chaotic noise, just completely drowning out a tiny quantum whisper.
And this actually brings us to a perfect summary from our sources. It says vibration, temperature fluctuations, stray electromagnetic fields, all can disrupt a quantum sensor's operation. So to actually harness quantum mechanics in the real world, absolute environmental isolation and profound physical silence are totally mandatory. You literally have to suck all the thermal energy out, stop all the natural jiggling of atoms, just so the quantum effects can clearly emerge without being destroyed.
Now, the physical bridge between our unsung hero, cryogenics, and the quantum tech revolution comes down to one really fascinating phenomenon: superconductivity. When certain materials get cooled down to these extremely low temperatures we've been talking about, their electrical resistance completely 100% vanishes. Electrons just glide right through them without losing a single drop of energy to heat. And this phenomenon is exactly what allows us to create the ultra-precise circuits we need for quantum bits, or qubits, and the highly sensitive components used in quantum measurement.
Which leads us to the machine that makes all of this a reality. Enter the dilution refrigerator. It is the heart of extreme cooling, and really the massive, complex physical embodiment of the cryogenic solution. It often looks like this beautiful, multi-tiered chandelier made of copper and gold wiring, but it's built for one solitary purpose: to pull almost all thermal energy out of its lowest stages. It uses a mix of helium isotopes to continuously push the temperature lower and lower. It's basically a high-tech protective fortress for the quantum chips inside.
So just how cold does that fortress actually get? Try 15 millikelvin. That is 0.015 degrees above absolute zero. It is almost unimaginably cold. But at this specific temperature, the quantum processor is finally sitting in perfect thermal silence. The superconducting circuits completely stabilize, the noise floor totally drops out, and the system can finally hold on to its fragile quantum states long enough to actually run calculations without immediately decohering.
It's really wild when you look at how this system is actually wired up. Microwave pulses are generated all the way up at room temperature by digital processors. But to even interact with the quantum chip, those signals have to travel all the way down through the heavily shielded, increasingly colder stages of the fridge. You've got these routing pathways where signals pass through attenuators and filters at every single temperature stage. This ensures that virtually zero thermal noise rides along the wire to reach the physical quantum processor, sitting all the way down at the very bottom, at that freezing 15 millikelvin mark. It is an absolute masterpiece of thermal engineering.
Section 1. Real-world magic. Squids.
Now, cryogenic quantum technology isn't just about futuristic room-sized computers. Let's look at quantum sensors for a second. Specifically, something called a SQUID, which stands for Superconducting Quantum Interference Device. This is not just theory, folks. SQUIDs are hallmark quantum sensors that have actually been around since the 1960s, and they're the exact reason those MRI machines we talked about actually work. Their sensitivity is frankly mind-blowing. We are talking about detecting changes in magnetic flux on the order of 10 to the negative 15 Tesla. That is literally a millionth of a billionth of the Earth's magnetic field. At that level, SQUIDs don't just detect metal. They detect the tiny biomagnetic signals generated by the electrical currents firing inside the human brain. That's what makes non-contact brain imaging possible.
But as amazing as they are, there's a huge catch. Even though SQUIDs are a fairly established technology, they have incredibly strict operating requirements. To get that mind-boggling sensitivity, a low-T SQUID still relies entirely on being bathed in liquid helium, just to reach 4.2 Kelvin. Even the newer, high-T SQUIDs require liquid nitrogen to hit 90 Kelvin. So all that incredible sensing power is fundamentally locked away behind the requirement for heavy-duty cryogenic liquids.
Section 2. The climax. Swap constraints.
So what's the major hurdle preventing quantum technology from being absolutely everywhere in our daily lives? In the engineering world, it's known as swap constraints, which stands for size, weight, and power. These are the real bottlenecks of the deep freeze. Cryogenics are massively power-intensive. The equipment demands heavy magnetic shielding just to keep out stray fields. All of this leads to a complete lack of portability and massive, massive operational costs. Because hey, as amazing as a quantum sensor is at detecting brainwaves or hidden underground tunnels, you can't exactly fit a liquid helium dilution refrigerator into your smartphone, right? Or strap it to a portable navigation device on a tiny drone. The required infrastructure is just way too massive.
So what exactly is the scientific community doing about this? Well, there is this massive quest underway right now to finally break free from the deep freeze. Researchers are actively hunting for exciting new ways to perform quantum sensing at normal room temperatures. One incredibly cool example is using nitrogen vacancy centers. These are tiny atom-sized defects inside diamonds. The fluorescence of these diamond defects actually shifts with temperature, which allows them to act as highly sensitive quantum nanothermometers inside living cells without needing a single drop of liquid helium. We're also constantly on the hunt for new materials like high-temperature superconductors, basically trying to push those operating limits higher and higher.
But, we just aren't there yet for everything. As one of our sources perfectly puts it, until then, where cryogenics are unavoidable, that confines those sensors to lab or fixed installations. And honestly, this is what you should really take away from this explainer today. For the time being, the incredible, world-changing power of quantum sensing and quantum computing remains physically tethered to the bulky, expensive, and power-hungry realities of extreme cooling. The cryogenic engineers making the freezers are just as absolutely crucial to the quantum revolution as the quantum physicists doing the math.
Which really leaves us looking to the future with a massive engineering cliffhanger. Will we actually find a way to miniaturize the deep freeze, creating tiny, ultra-portable cryogenic coolers? Or will major breakthroughs in material science discover a totally new way to bring the fragile magic of the quantum realm all the way up to room temperature? The answer to that question is ultimately what will determine whether quantum technology stays confined to high-tech research labs or becomes as ubiquitous as the microchip in your pocket. Thank you so much for joining me on this explainer, and definitely keep your eyes on the incredibly cool world of quantum engineering.